Hello my dear students, good morning to you all. So, in my last class I was explaining about solvent extraction. So, there we understood what is meant by solvent extraction. So, in solvent extraction, so two immiscible liquids are shaken together. That means immiscible means if you take chloroform and water in a test tube, then you can see or understand what is meant by immiscible liquids. That means one will be a organic solvent and another one is aqueous solvent. There clearly we can see the separation of organic solvent and aqueous solvent. Okay. So, such a type of liquids are called as immiscible, they are not miscible. They will not combine with each other, they are not soluble with each other. So, that is why they form immiscible liquids. So, in solvent extraction, as I said in class, so we are going to shake the two immiscible liquids together, so that to separate one component or many components. Okay. So, even if there are many components, so then also we can separate it. So, what happens when we shake together two immiscible liquids is the more polar solutes dissolve preferentially in the more polar solvent. Okay. So, polar compounds which are present in our compound. So, all those polar compounds will be terminated towards or move towards the more polar solvent and the less polar solutes in the less polar solvent. Okay. So, this is what is going to happen in solvent extraction. So, the three most common types of extractions are, one is liquid extraction and liquid solid extraction, and the third one is acid base solvent extraction, which is also known as chemically active extraction. We call it as chemically active extraction. Okay. So, this is what we were discussing or I was explaining in my previous class. And also I said about the solvent extraction or liquid extraction, which is considered to be the most popular and versatile technique of separation. That is because of two reasons what I mentioned. So, that is it does not require any sophisticated apparatus or instruments except a separating funnel. Only a separating funnel is needed, other than that no instrument or nothing is needed to carry out solvent extraction. And the second point was, the separation can be carried out in macro scale as well as on micro level. Okay. So, even if there is a very small amount of compound, so that also can be extracted, or even if it is in macro scale or in grams or kgs, so that also can be done with this solvent extraction. Okay. So, in this session, so I am supposed to explain you about what is the basic principle of solvent extraction. Okay. So, the solvent extraction is governed by the Nernst partition or distribution law. What is Nernst partition or distribution law? It states that at a constant temperature and pressure, a solute S will always be distributed in the same proportions between two particular immiscible solvents. Okay. So, here solute is the thing which has to be extracted, and this solute is present in any one of the solvent which we have used. Okay. So, here two solvents are there. So, those two solvents are immiscible with each other. So, in one of the solvent the solute is present, and that solute is going to distribute or get separated in the same proportions between two particular immiscible solvents. Okay. So, at what condition this is going to happen? This is going to happen at a constant temperature and pressure. So, this is what Nernst partition or distribution law states that. Okay. So, here solute is represented as S, which will always be distributed in the same proportion as I said. Okay. So, the ratio of the equilibrium concentrations in the two phases is constant. So, that constant, let me call it as Kd. Okay. So, here Kd means partition coefficient or distribution coefficient. So, here I have represented it in a mathematical form, where this is a solute which is present in the organic solvent, and this is the solute which is present in the aqueous solvent. Okay. So, this is how the ratio of the equilibrium concentration in the two phases which is constant is represented in terms of a mathematical equation. So, and let me call this equation as equation number 1, and here what we have to notice is so Kd is independent of the total concentration of the solute, okay. Whereas in practice the solute often exists in different chemical forms due to complexation, protonation, dissociation or polymerization, okay. Suppose during the solvent extraction, if there is a formation of complex, okay. So, a complex is a inorganic compound which is formed with the metal and ligands, okay. So, what it is we will see in our later classes, you will be studying coordination compounds. There we will understand what exactly a complex means, okay. There is a chances of complexation during this solvent extraction, and there is a chances of protonation, that means when element or the molecule it loses the protons or gains the protons. So, there we can observe the protonation and also dissociation or polymerization. So, all these chemical forms will exist during the solvent extraction in practice. When we will do it in practical classes, definitely we will observe all these type of chemical formations or chemical changes. Therefore, the term distribution ratio or partition ratio, which I call as Kd, will be represented as D, which is given by the expression D is equals to Cs in organic solvent divided by Cs in aqueous solvent, where Cs represents the total concentration of all forms of the distributing solute S in each phase, okay. So, each phase is here we can observe two phases, one is organic phase and another one is aqueous phase, okay. So, here in organic and aqueous phase, so what is the total concentration of all the forms? So, that is represented with the help of distribution ratio or partition ratio, which is called as D, and this mathematical form is named as equation number 2, okay. So, if no interactions involving solute occur in either phase, then Kd and D. So, what I have written here. So, this Kd which is also called as partition coefficient, and here D I have represented it in D. When in practical classes the solute often exists in different chemical forms, at that time to make it simplify I am taking it as D, okay. So, suppose if no interactions involving solute occur in either phases, so then Kd and D would be identical. That means, if there is no complexation, no protonation, no dissociation or polymerization has been observed, so then it is understood that Kd is equal to D, that means both are equal, both are identical. The solute with large values of D will be essentially quantitatively extracted in the organic phase. Okay. So, this is what the basic principle of solvent extraction explains about. And next what we have to see is the extraction efficiency. What is meant by extraction efficiency? So, the efficiency of an extraction depends on two concepts, that is the value of distribution ratio, and the second one is the relative volumes of the two liquid phases. Okay. So, always efficiency means that, so how economically or how good results are obtaining. So, that is what is meant by extraction efficiency. Efficiency means in what percentage, in what good terms we are achieving the extraction. So, that is what is meant by extraction efficiency, and it depends upon two terms, so that is the value of distribution ratio and the relative volumes of the two liquid phases. Okay. So, the percentage of solute extracted which is represented as E, or extraction efficiency, is given by this equation, where E is equals to 100 D divided by D plus V aqueous divided by V organic. Okay. So, what is V aqueous and V organic here is so these two are the volumes of the aqueous and organic phases respectively. V aqueous means, so it is the volume of aqueous phase, and V organic means it is the volume of organic phases. Okay. So, this is what or in this way we are going to calculate the extraction efficiency. Okay. And D is nothing but distribution ratio or partition ratio. Okay. So, in this equation D is nothing but distribution ratio or partition ratio, and V aqueous is the volume of aqueous phase, and V organic. So, this is V org. So, this is the volume of organic phases. Okay. So, this is what is meant by extraction efficiency. And next, moving on to the application of solvent extractions. So, mainly we can classify the application into two different classes, that is, one is in qualitative analysis and another is quantitative analysis. Okay. So, what is meant by qualitative analysis and quantitative analysis, that we have seen in this unit. So, the initial states of this unit explained what is meant by qualitative analysis and quantitative analysis. Okay. So, now we will see the applications of solvent extractions in qualitative analysis. So, the solvent extraction is used in qualitative analysis in order to make a test more sensitive. Okay. So, why we will use solvent extraction in qualitative analysis is, so the reason is the solvent extraction is used in qualitative analysis in order to make a test more sensitive. Okay. So, as we all know, if you see the applications of solvent extraction, the solvent extraction is a versatile method of separation. So, this I said in the beginning of this topic, that is solvent extraction. It is versatile method, very well used, that is because it does not require any sophisticated apparatus, or the separation can be carried out in macro scale as well as micro level. So, that is why we call the solvent extraction as a versatile method of separation. So, it therefore find extensive applications in analytical chemistry for separating and determination, and also in inorganic chemistry at preparation scales. Okay. So, that is what the application of solvent extraction explains about. So, we will see some examples. So, here cobalt 2 ion and ammonium thiocyanate forms a blue color tetrathiocyanate cobaltate complex. Okay. So, the formation of blue colored complex can be more easily seen by adding few drops of amyl alcohol. Okay. So, if we add few drops of amyl alcohol, so this is an example where we are using it for the separation of cobalt 2 ion and ammonium thiocyanate. Okay. So, this composition of cobalt 2 ion and ammonium thiocyanate will form a blue colored tetrathiocyanate cobaltate complex. So, the formation of the blue colored complex can be more easily seen by adding few drops of amyl alcohol. So, the complex is further extracted to the organic layer by shaking. Okay. So, this is one very good example in qualitative analysis where we are going to use it for the qualitative analysis in order to make a test more sensitive. Okay. And the second application is in quantitative analysis. So, extractive spectrophotometric determination of metal ions. So, this is one very important application of solvent extraction. So, what we are going to do here is, so the metal ion in a mixture will form selectively a colored complex with the chelating ligand. Okay. So, this is what when during the formation of complex is going to happen. During the formation of complex, when metal ion comes in contact with the chelating ligands, we call them as ligands. So, there we observe a mixture which is formed, okay, with a selectively colored complex. Each metal has got its own selective color. So, the metal ion in the mixture forms selectively colored complex with the chelating ligand. The complex is extracted in the organic phase and concentration of metal ion can be determined spectrophotometrically. So, this is the application that to especially the quantitative analysis application of solvent extraction. For example, the extractive spectrophotometric determination of lead as thiazone complex. So, the pH will be maintained at 9.5 and the lambda max is 510 nanometer. So, the solvent extraction will be carried out with the help of chloroform. Okay. And in this copper and zinc which will be present up to 10 mg, they will not interfere. Okay. And the second example is solvent extraction and volumetric estimation of iron 3. Okay. So, the estimation of iron 3 also could be achieved by solvent extraction. How we are going to do it is, so iron 3 can be separated from most of the mono and divalent cations by extracting it from 6 fluorohydrochloric acid in diethyl ether. Okay. So, then what happens, the different sorts of complexes with the help of ferric chloride is going to get, or it is going to formed, and it is extracted into ether layer, and further the ether is evaporated, and then the iron 3 is reduced to iron 2 and it is titrated against 0.1 normal of potassium dichromate using diphenylamine as indicator. Okay. So, this is one example. You need not to worry much about the formation of complex, how the complex is going to form and how the reduction is going to take place, and how we are converting ferric into ferrous. So, all these things you need not to worry much, you just go through with the application part of solvent extraction, that is more than enough. Okay. And the next interest of topic is errors in quantitative analysis. As we all know, we are human beings, and definitely while performing the experiments we will undergo certain mistakes. So, it might be classified as determinate errors or indeterminate errors, or because of environmental factors, or methodic error, or operative error. Sometimes even operative errors also takes place. Okay. So, all these has to be analyzed to reduce the errors and also to get accuracy and precision in performing the experiments. Definitely these errors should be reduced as much as possible. We have to reduce the percentage of errors. Okay. So, to reduce that, first we should know what is meant by error and what are the ways for an error to occur. If we know about that, definitely we can think over how to reduce the errors. Okay. So, we will see what is meant by errors in quantitative analysis. So, errors is defined as the numerical difference. So, it is a numerical difference. Errors are numerical difference between the observed or measured value, which is called as x naught, and the expected or true value. There will be a true value always. Say for example, if we are doing a melting point or boiling point experiment, definitely for each compound, unless until the compound is already known. If it is a new compound, definitely we have to predict, we have to check it, and we have to say the melting point of this compound is so and so and the boiling point is so and so, that we only have to give, unless until if it is novel, if it is new. But suppose, say for example, even though if it is new, for example, we know the melting point of urea. Urea is in solid state, and we know the melting point of urea, and if we have synthesized any derivative of urea, definitely I will be expecting the melting point which will be near to the expected value or true value, that is urea, because this is a derivative of urea. So, that is why I will be expecting the melting point which has to come near or closer to the known value, known melting point of urea. Okay. I hope you understood this. So, that is why always there will be a expected value or a true value. So, error is defined as the numerical difference between observed, what I have observed or measured, and the expected or true value. Okay. So, this is what is called as the error. The absolute error which is represented as EA in a measurement is given by EA is equals to observed or measured value minus true value or expected value, and it is represented as EA is equals to x naught minus XE, where x naught is the observed value, XE is the expected value. Okay. So, this is how we are going to calculate the absolute error. Next, we will see how we are going to calculate the relative error. So, relative error is represented as ER, and the measurement is given by ER is equals to x naught minus XE. Okay. So, here x naught is the observed value, XE is the expected value divided by expected value XE. So, this gives relative error. Okay. And next is relative error of measurement in percentage. We have to convert this into percentage. Always whenever we talk in general, we say it in terms of percentage, okay. Whatever the issue is, everything could be converted into percentage. Say for example, the percentage of COVID patients in Dakshin Kannada district or in Bantwal taluk, or we can take it in our college itself. Percentage means total strength of the students and how many are infected divided by the total strength into the percentage means into 100, that gives the percentage. In the same way, so relative error of measurement in percentage is nothing but, so for this relative error, if you multiply it with 100, this gives us the relative error of measurement in percentage, okay. So that is ER is equals to x naught minus XE divided by XE into 100. Also it can be represented in parts per thousand. So then we have to multiply it with the 1000, okay. So then it is represented as a parts per thousand, okay. Errors may be introduced in a measured value of property by number of sources. The errors in the measured value will affect the accuracy and precision of the measured value, and hence the reliability of the data, okay. So that is why we have to reduce, we have to avoid the errors. So these errors will affect the accuracy and precision of the measured value and hence the reliability of the data. So that is why it is must and should we have to reduce the percentage of error, okay. So I am going to stop it here, and in my next class we will understand about the classification of errors. As I said, one is determinate errors and indeterminate errors, and what are the different types of determinate errors, and what is meant by determinate errors, and how to control or how to reduce these errors. So all these things we will discuss in my next class, okay. So thank you, dear students.